a demonstration of eddy currents. Now we have a piece of steel, and you see it's very strongly attracted to the magnet. Now, aluminum, this is a very thin sheet of aluminum, but there's no attractive force at all to the magnet. Now, what we're going to do is we're going to put this, hang this piece on here so that it can swing. And now we're going to put another magnet. These are two opposite poles of a magnet, creating a magnetic field between them, on both sides of this plate, but not touching it. And then we're going to try once again to swing the plate through there. Now, it didn't touch at all. Nevertheless, the interaction with the magnetic field caused it to stop. And try it on this side too. It just stops. It's important that it's not, you can't maybe see, but there's space on both sides. It's not anywhere near to touching those magnets. Okay, so this one, we can also try this thing, more or less the same, but it's got these cuts in it like a rake. And try the same thing, we let it go, and it doesn't feel that braking motion at all. Okay, one more. Something more or less the same, but they're connected at this end. Try the same thing. It stops, not quite as quickly as the full plate. Watch again, it goes through and then comes back. It stops, whereas this one, it just stops right away. Okay, so we would like to understand how this works. So what we've drawn here is a picture looking sort of like in the plane of that plate of aluminum. So we see the magnetic field going down into the screen. So a little X makes it go down. And we've drawn a loop here that is a path within the aluminum sheet. So a loop of metal in the aluminum sheet. Now that is moving to the right, so it's like we're imagining that loop moving across. Okay, so because it's moving across, I've drawn the magnetic field so it's getting stronger and stronger as you approach the middle. So the darker green is stronger magnetic field, and that's sort of what the field is like between those poles. So as the plate goes into it, the magnetic field strength is increasing. And then we know if the magnetic field strength is changing, that you get a change in the flux, and it should cause a current in that loop. So let's look at directions a little bit here, because the directions are very important in this example. So I've defined what we'll call the positive direction for the induced EMF so that it would push a current counterclockwise around the loop. And so then you imagine what's the area, what's the direction, the area vector. So you take a cap and you turn it in that direction counterclockwise. The cap would come up away from the screen. So that's pointed out. So I've drawn that here. Okay. So we see that we have the area and the magnetic field are in opposite directions. That means that the flux, which is the dot product of the two, is negative the product of their magnitudes. That in turn implies that the induced EMF should be, because the two negative signs cancel. All right, now we know the area of that loop is a constant. So this should just be the rate of change of the magnetic field times the area. And since the magnetic field strength is increasing as the loop moves to the right, you get stronger and stronger field, this number should be positive, the rate of change of the field with time. Therefore, this whole thing should be positive because the area is positive. So we find that this is a positive number, meaning that indeed the current will go in the direction we call positive, which is this way. Now, the nice part is that now we can think about forces. We have a current in a magnetic field, so it feels a force. Now, this one out here isn't feeling any force because there's no field there. The same for the other three. But this one, using the right hand rule, put your arm in the direction of the current and your palm facing the field and your thumb moves in the direction of the force. So this feels a force this way, opposite direction of the velocity. Okay, so that's the braking force that it felt. The same thing would happen down here. The field is still increasing. Oops. So these currents are still going this way. Apply the right hand rule again. This one will still be in this direction. This one will be down. This one will be up. And this one will be to the right. Okay, so it seems like that would all cancel each other. And it's true that the top and bottom do cancel each other. It's symmetric in that direction. But this one and that one don't, because the field strength is stronger here and weaker over here. So the one on the right has a stronger field than the one on the left. And they both have the same current. So that means that this vector here has to be stronger than this one. So even though there's a force on this side of the wire to the right, the leftward force is greater, and so the net force is to the left still. Now you might think then that when the loop is on this side, that now the force would be to the right, but two things switch in this case. On this side, we're now leaving the region with strong magnetic field here in the middle. So the field strength is now decreasing. So now the rate of change of the magnetic field strength with time is decreasing. That means it's a negative number. And that in turn implies that the EMF is negative. So the current, in fact, goes this way. Of course, that flips the direction of all the forces. Now the stronger force is here on the left side, but its direction has changed. So instead of the left side having a force to the right, the left side now has a force to the left. This one wins because it's in the stronger field. So we still have a force to the left in the opposite direction of the velocity. Okay, so this is these currents that happen inside of a conductor as it's moving through a magnetic field are called eddy currents. And this is called eddy braking. In fact, my understanding is they use these as brakes on a train. So you have giant steel wheels on the train and they put magnetic field on each side of it, and that just causes it to slow down without any friction. It burns up heat in the wheels get hot, but there's no friction. Now, this leaves us with a question of what's the difference between the rake-shaped one and the one without the cuts in it. The analysis of this is slightly more complicated, but it has to do with the shape of the loops. So in this one, you can see that you can't have a current loop through here because it's broken. So the current loops have to be small here. Whereas in this one, you could have a big current loop. Now, unfortunately, I wish this thing had been made so that it had the same area. They could have just as well have been made like this, where there was just a tiny slit in there instead of being a big gap. And we would have had the same effect that this one would still have less braking force on it, even if it had the same area. So the key is that these smaller circles, for some reason, have less braking force than these big ones. The analysis of that is a little bit complicated, a little bit actually beyond the scope of the course, but I'm going to go through it anyway, just as a quick example. Don't worry about the details if they seem unpleasant. So what I've done is I've drawn here a square. And I've divided it up into a sequence of loops. So one of these right there, and I've taken that out and put it down there. So imagine taking this square and just slicing it up into a bunch of little square loops. Each one has a length 2a on a side and a thickness dA. Now that loop, we could calculate, we've done a little bit about resistance. You could calculate the resistance of that loop. It has to do with the distance around the loop, the cross-sectional area of the loop, and number B here is the thickness of the metal, and the electrical conductivity. All right, now, and I've simplified the magnetic field a bit to make it easier to calculate. So what we have here is a magnetic field which is just gradually increasing as we go across. Here we have a picture of the magnetic field versus the position. So it's just slowly going up at a constant rate, then it's constant here. All right, and we'll call the rate, this slope here, just S, to not take up so much space. So it's how quickly does the magnetic field as you change position. And of course, this loop is going through and feeling a different position at each time. Okay, so if we want to try to find the rate of change of the magnetic field with time, we use the chain rule. So it's the rate at which the magnetic field changes with position times the rate at which the position changes with time, which is just the velocity that this loop is moving, times the slope. So that's nice. So we can get it, the rate of the field changing with time nice and simply. Again, we've taken these two to be in opposite directions, the magnetic field and the area. So that gets rid of this minus sign here when we're calculating the induced EMF. It cancels it out. Okay, so then we go ahead and calculate. We have the rate of change of the magnetic field times the area. The area, of course, is just 2a times 2a, so 4a squared. Now we want to calculate the current. I'm going to call it DI, just because we're going to have to add all these up, so I'm thinking this is a little current going through here because it's very thin. So it's a very thin wire in essence. and so it doesn't carry much current. And we're going to add them all up in the end. So the current should be the voltage divided by the resistance. We just got the induced EMF, which is the voltage that's driving it. We calculated the resistance, we just combine them, and we get this nice result. Now that allows us to then calculate forces. We know the equation for force. It's the current times the length of the wire times the magnetic field. This is assuming that the field and the currents are perpendicular, which in this case they are. Okay, so first thing we remember is that the force on the top and the bottom parts of the loop cancel each other. So all we really need is the force on the left and right side. Okay, so the force on the left side here is this. The force on the right side is that. So the length times the current times the field. The length times the current times the field. Now I've written it, the field as the field evaluated at a certain position. So there's two different positions. We simplify it, we collect that together, and we say, oh, that's the change in the field. Well, that should be the rate at which the field is changing with position times the change in position. So that allows us to write it in terms of the slope again. So we find the net force in terms of the current, and then we just put in the current that we found before. So mostly just substitution there. Okay, so the last step is to add up the force of all of those different loops. So we're really just integrating over this constant A from 0 up to half the length of so if this whole thing is L, A is the half length, so we want to go from 0 to L over 2. And after you've done that, you get this nice result here. So what it is, I took the force, it's proportional to the length to the force. That's the area is the length squared, so this is the area squared. So I divided by the area, so we've got the force per area, and that somehow normalizes it so that we don't get confused. So how much force can you get from a certain area? And what we find is that it still depends on the area. So the force per area still increases as it gets bigger. So then if we go back and think about these configurations, we see that these small loops, or let's do it like this. Say we had 4 small loops, or I don't want to do this. Well, they should really be rectangles, right? So 4 squares of a certain area, and then 1 big square with the same area. Okay, so the force per area of this one is proportional to the area. So since this area, the size is twice as big, or 4 times as big, you get 4 times as much force for the same area. Okay, remember we divided by the area already, so it's the force per area, which is proportional to the area, which sounds a little funny. Usually things are proportional to the area, but this wasn't proportional to the force, wasn't proportional to the area. The force was proportional to the area squared. Okay, so that's why this is more effective. You get a bigger loop. The force goes as sort of like the square of the size of the loop. Okay, so if you double the size of the loop, you get 4 times as much force. Okay, so let's look at one more example here. So this is an induction stove. So this is just a regular iron skillet. It's started out cold with a bit of water in it. And so an induction stove operates by induction, which is what Faraday's law is about. So what the plate is it's essentially the same as one of those wireless phone chargers. So it's just a loop of wire with an oscillating current in it. That creates a magnetic field coming out of the plate, perpendicular to the plate. So if you put something on top of it, that magnetic field will pierce whatever it is and oscillate. And you see it's already starting to get steamy and will be boiling shortly. You can see little bubbles coming up already. We don't need to watch it anymore. It will be at a full boil in no time at all. Okay, so what's happening, like I said, the stove, this little hot plate, if you will, creates a magnetic field. So I've drawn that in this green color coming up through the pan. This is why it's important that the pan isn't aluminum, because aluminum tends to exclude the magnetic field easily. So the iron, on the other hand, conducts magnetic field really well, so you don't lose any of the field. So then we, of course, if we have this fluctuating magnetic field, that creates a fluctuating electric field circulating around it. That electric field, in turn, causes a current. Now, the current delivers power as heat because of the resistance of the metal. So if you remember, P is IV, which you can write as V squared over R, or I squared R. So because there's resistance in the pan, the current causes power to be burnt up in the pan, so to speak, and it heats up. It's very, very simple. And very effective, because you're not making heat until it gets into the pan. So the stove itself doesn't get hot. It's the pan that gets hot.